Hello, class. I hope everyone's having a great week. We're going to finish our strategies or our skills that I'm trying to just show you guys a little bit about with problem solving. So we're going to look into some problem solving things. This is something we've been doing throughout the year. I've been just kind of introducing it a little bit at a time, kind of without making it a big point, but we're going to spend a whole day today just focusing on it. So I'm just curious for you guys to start thinking about word problems. Really is a big part of problem solving. So when you see a word problem, what is the first thing you do? So maybe some of us freaked out. I know I was always nervous when I saw word problems because all of the times I didn't understand them or they had too much information. So do we read it? Do we try to draw a picture? Do we immediately ask for help? So what are the first things that we do when we see word problems? And then what are the steps that we followed when solving our heat problem? So not too long ago, I tried to outline things for us when we did our heat problems. So the first thing we did is, of course, read them. And then we wrote down given, what we were given, our equation, and then our work using that equation. So we're going to kind of go through those same steps with problems or different things that we have never seen before. Because a lot of the times in science, you might be given something, maybe an equation or a problem, and you're given the variables and the equation. You don't necessarily need to understand it all, as long as you know how to put those numbers into an equation you're given. So, and maybe understand that equation and how it works a little bit. So we're going to work through that today. So list and practice the steps when we're going through a science problem is the big thing. Here's a quick video that I thought was good. This is a strategy is read the question with a little bit of a bad word, but it's a very good video. I really thought it outlined and talks through things very well. So the steps that we're going to look at today, step one, we see a problem. We got to read the question carefully, really, really carefully. This is a very common mistake is people don't read very closely or they miss things. So we want to make sure we read it carefully, know the information we're given, and especially know what's being asked of us. Sometimes, and I do this, is I see a question, I maybe see some variables I know, and then I just assume what the question is at the very end, rather than really slowing down and reading it very carefully. This is an important time to slow down, especially if we like to work very quickly. Step two is draw a picture. So we want to make sure we're able to understand what we're being asked by drawing a picture. It can help us visualize what's going on as well. We want to put numbers and variables in that picture as well. I think this is an important thing too. If we visualize the situation, it can be very helpful. So especially in science and like physics, when we can picture what would happen if we dropped a ball, we can think about, okay, I have a ball in my hand and I drop it. What's that? What would that feel like? Have I seen that before? And I can use my real life examples and experiences to help me understand the problem as well. So if you can, think about how this would work. Step four is think about a plan to solve it. A lot of the times this will require needing equations. So if we think about a plan, we can think about some maybe equations we already know or how we might want to try to go about this. And then maybe start searching for equations and then write down the one we need. Of course, the last thing we do, the work step that we have done, we can crunch the numbers. This is a funny thing that says we need to crunch the numbers before they can crunch us. So just crunch the numbers is another way for putting our numbers, our variables, into our equations and getting an answer. So we have a lot of work to do before we can actually start doing our numbers and our equations. And then the last thing that's important is double check. This visualization step is important during our double check because if we get a number that seems really, really, really big or really, really small, we know we probably did something wrong. So that's always important. So let's look at an example together. An airplane accelerates down a runway at 3.2 meters per second for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before it took off. So read the question. What is it asking us? Well, we're actually trying to find the distance it traveled before it left the ground. Let's draw a picture. Now, don't make fun of my picture here, guys. It's not the best, but we have an airplane going down a runway. I put our acceleration is going this way. I said our time is 32 seconds. So I took these numbers and put them into variables. And we're trying to find our distance traveled. So I'm going to call that x. And then the other thing that didn't get told that maybe I intuitively thought is I've traveled in an airplane before. We usually, when we turn on the runway, we stop for a second. So we stop all the way, we're resting, and then it accelerates really fastly. So what this says is our initial velocity, our v sub naught, is 0. So we're starting at 0. We're starting from a stop, and we're accelerating. So step 3 is to visualize. So if anyone has sat in a plane before, this might be a little bit easier. It helps us make sense of the numbers and what our answer will be later. Then let's make our plan. So mostly this means finding the right equation. A lot of times science, or especially if we're doing tests, science tests very quickly, will give us an equation sheet or a formula sheet like this. So we have all this stuff, which can be very overwhelming to think, oh my goodness, how do I even find the right thing in all of this? Well, part of it is we have to know what kind of problem we're being asked. So thermodynamics is for heat. That's another word for heat. We're not being asked about heat. We have fluid dynamics. That's with like water. We're not really being asked about fluid dynamics. Linear momentum and collisions. That sounds closer. What we're looking at is what's called a kinematic equation, which is like the study of motion anytime we're moving. So let's focus on just this group of equations to kind of help us in this problem. So let's go back to our thing here. So we got to find one equation from the variables we wrote down to help us. So maybe we could find something with x equals in our list of stuff. So we can see x equals here, but we don't have our initial or our final x, so that one doesn't really help us. Oh, we have an a, but we don't have a velocity final. Whoa, we have an x here and an x here. So this x only has x sub naught and our velocity, our final velocity, but this one has our initial starting point, in x, our initial velocity, time, acceleration, and time. So this one has a lot of the variables we're given. So let's try to use that. So that'll be the one we pick. When we write an equation, we're going to focus on this one. This says our initial position. So if we started, most of the time we start at 0, so this will be 0, but maybe we started somewhere else. We could put a different number in. We're going to put 0 in. Our initial velocity we said was 0. We have time, 32 seconds, and we have acceleration and time. So now we get to crunch our numbers. 0 plus 0 times 32, which is going to be 0, plus 1/2 times 3.2 times 32 squared. And when we crunch our numbers, we find that our plane traveled 1,632 meters before it took off from the ground. Now, double check, does this make sense? I think it does. It would not make sense if it was really, really small. So let's say our answer was like 2. We traveled 2 meters before we lifted off in the air. That one wouldn't make sense because if anyone of us have been on a plane, it usually takes a while for us to get moving and actually get off the ground. So let's look at another example. Oh, this was supposed to pop up a little bit later. So a feather is dropped from the moon, or dropped on the moon from a height of 1.4 meters. The acceleration of gravity on the moon is 1.67 meters per second. This should be squared, not to the 2 squared. Determine the time for the feather to fall to the surface of the moon. So read the question. What is it asking us? We're trying to find the time for the feather to hit the ground. Now, this is when my picture comes in. Again, I was drawing this on my computer, so my feather doesn't look too good, but this is supposed to be a feather. So we can say that our feather is here. I called this distance x because that's our height. I called it x instead of h. Our acceleration, we said, on the moon from gravity is 1.67 meters per second squared. Again, anytime we drop something, it actually has an initial velocity of 0, and we're asked to find the time. So I put time with a question mark. All right, visualize. This helps us make sense of our number later. When we drop the feather, does it take a long time to hit the ground, or does it fall really quickly? Let's make a plan. Let's look back at our equations. So going back to our equation sheet, I think we're going to use something very similar to our other one. Actually, let's use the exact same equation because we're given similar variables. We're given x this time. We're given an initial velocity, a time, and an acceleration. Sorry, we're not given a time, but we're given an acceleration. So let's try to use that same equation from before. This time, though, when we crunch our numbers, we plug in a number for x as 1.4, x sub naught is 0, velocity is 0, and then we have 1/2 times 3.2. Sorry, that acceleration should be 1.67. I apologize. And that means this number is wrong too. Sorry guys, this should be 0.8, and I have a couple wrong numbers. So we'll do this, I'm going to do this real quick and then continue our video. My apologies guys, at the end of the year and Mr. Max is still making mistakes in his presentations. Some things will never change. So what I did is I multiplied 1/2 by 1.67 and got 0.8, and then I divided each side by 0.08 to get 1.75. Then I took the square root on each side and found that our time was 1.3 seconds. So it took 1.3 seconds for it to hit the ground. Does this make sense? I would say yes. Like we said, on Earth, our feather falls and it takes a while to hit the ground. So I would say it would make sense. All right, another example. This one is about thermal expansion. So when we heat things up, they actually expand, but we want to find out how much they expand. So this says if a meter pole starts at 2.5 meters, the temperature changes by 15 degrees Celsius, and the expansion coefficient of metal is 11 times 10 to the negative 6 meter per degree Celsius. How much does the pole change? So we're trying to see how much our pole changes. What is our question? Yeah, how much does our pole change in length? Draw our picture. Again, I'm not the best artist, but I did my best. So we have our change in temperature. Our delta T is 15 degrees C. We're going to call this our length is 2.5 meters. And our expansion coefficient is alpha, 11 times 10 to the negative 6 meters per degree Celsius. So let's visualize this. If we have a pole, it heats up. Is it going to expand a lot? Are we going to see it go the difference of a whole meter or just a little tiny bit? This helps us make sense. Our plan, so let's look at this. So we're dealing with heat this time. So let's go back to our thermodynamics part of our heat and heat transfer methods. So let's look around here. I'm not really seeing anything that has L or alpha or delta T. So after searching, I finally found something that's going to help us. So we want to find the change in our length. We have alpha, we have an initial length, L, and a delta T. So this has 3 of our variables that we need, and what we're looking for is what it's equal to. So that's our equation we're going to use. That's our plan. And our equation says that our delta L, our change in L, is equal to our alpha times our length times our delta T. So this is when we crunch our numbers. We plug in our alpha, we plug in our L, we plug in our delta T, and then just multiply them all together. And we found that our change in length is 0.0004125 meters. So a very small amount. Does this make sense? Yes, because we didn't expect to get a big number. We wanted to get a small number. So I want you guys to try this one on your own. This is your exit ticket. Follow our steps as always. Read our question carefully. Draw a picture. Visualize. Think about a way to solve it. I put all of our related equations here, and then we're going to crunch. But let's look at this together real quick. So our question is how much pressure is experienced by a scuba diver at 30 meters? So we're given 30 meters, we're given a depth, we're given a density, and gravity. So the equation we're going to use is going to be this one, P is equal to rho GH. So I want you to try that. If you have questions, let me know.